is Galton, define the quincunx in order to provide a tool to help understand the normal distribution. Let's dig into it. Let's see the details of the normal distribution. Normal distribution is a probability distribution, one of the many probability distributions used in statistics, and is the most popular of them. The characteristics of the normal distribution is that it is a symmetric distribution. The mean of the distribution is in the center of the distribution, and then there is an equal probability for values that are above the mean and values that are below the mean. In this case, we've got a probability distribution with a mean of 100 and a standard deviation of 10. The mean and the standard deviation of the distribution are the only two parameters we need in order to fully define the distribution. Now, on the y-axis, you've got the density of the distribution, which is probability density. We are not going to explain in detail the concept of probability density. Suffice it to say that the more the value in the y-axis, the higher the probability. So in this case, we have that 100, which is the mean, is the most probable value, because the point that connects 100 to the y-axis is the higher in the curve. Let's now go back and explain what is probability. So probability has three elements. First element is an experiment. But by experiment I don't mean an experiment conducted by a researcher, rather a random process, like tossing a coin or rolling a die or playing the roulette. The second element is the possible outcomes of the experiment. In the case of tossing a coin, the possible outcomes are heads and tails. In the case of rolling a die, the possible outcomes are 1, 2, 3, 4, 5, and 6. And in the case of playing the roulette, the possible outcomes are values between 0 and 36. The third element is the credence or expected frequency for each possible outcome. For example, in tossing a coin, we've got the two possible outcomes are heads and tails, and if we don't have any additional information, though both of these outcomes are equally likely. So we've got two possible outcomes, and for each of these outcomes there is a 1 in 2 or half or 0.5 probability of occurrence. For the die, we follow the same criterion, and because all the values are equally likely, we determine that the probability for each of the possible outcomes is 1/6. And for the roulette, there are values from 0 to 36 are probable. So for each of these values, we said that there is a probability of 1 in 1 divided by 37. So that is probability, but the examples I provided here, they refer to discrete variables, variables that can take discrete values like 1, 2, 3, or heads, tails. But they are continuous variables, and the case of the normal distribution is a continuous variable. So it's a bit more complicated when we talk about continuous variables in probability. So we still have the same elements. The First one is the experiment and random process. Now, the binary outcome of tossing a coin or the 6 possibilities in rolling a die, they don't work very well as metaphors to understand probability distributions in continuous variables. I developed a metaphor called the drone delivery metaphor. So the experiment in the drone delivery metaphor is one drone landing. I will go into this in a minute. The second element is the possible outcomes. And in this case, because each individual value actually is impossible to happen. Why? Because in a continuous variable, there are infinite number of values between each value. So for example, between 0 and 1, you've got 0.1, 0.2, but you also have 0.15, then you have 0.152, then 0.1528, then 0.1527, and so on and so forth. So if you have an infinite number of possibilities to assign probabilities, then your probability rounds out of resources and you cannot assign to anything. So in this case, it doesn't make sense to talk about assigning probability to a specific value. We assign probabilities to intervals of values. So one interval has the lower bound is -infinity and the upper bound is -3. Now this is arbitrary. We can choose any other interval, but we are going to go from -infinity to 3 and then on the other extreme to 3 to infinity, and then we after that we create intervals that have the same length. So for example, from -3 to -2, then from -2 to -1, then from -1 to 0, then 0 to 1, then 1 to 2, then 2 to 3, and then 3 to infinity. So these are possible outcomes, but we can define it in different ways. This is just for convenience. And the third element is the same. We give credence or expected frequency for each possible outcome. In this case, the outcomes are the intervals. Now, how do we do that? In the case of the rolling the dice, it was easy. We gave 0.5 to each of the possibilities. But in this case, it's not easy. So let's return to the drone landing metaphor I mentioned at the beginning. Let's consider we've got a city in which there is a new pizzeria that is delivering pizza using a drone. So we want to know where in the city the drone will land first. The assumption is that nowhere in the city there is more preference for pizza than any other part of the city. So basically everybody prefers, everywhere in the city the preference for pizza is the same. So where is the first takeaway request will come from? Well, this graph tells us a bit about that. So one useful way of categorizing this city is to say that in the middle, in the center of the city, we call the kilometer 0. And then if we go from there to the east, then we've got kilometer 1, kilometer 2, kilometer 3, 4, 5, 6, and interestingly, this is an infinitely long city, so there is no boundary. But because we know the probabilities beyond these are negligible, we are happy to keep it up to 6. And if we go the other way, if we go west, then it's the same. This is 1 kilometer, 2 kilometers, 3 kilometers, 4, 5, and 6, but we add the negative sign. Okay, and these bars, what they show us is the population, how the population is distributed in the city. So it's showing that between -1 and 1, there is most of the population. There is some decent amount between -1 and -2, likewise between 1 and 2, and then a little bit less, or much less in -2 to -3, which is the same as 2 to 3. Beyond that, the population in those areas are very, very small and possibly negligible. So obviously, in parts that there is more population, there is more chance that the drone will land there. So how do we determine the probability of landing in each area? Well, we have to use a formula, which is the formula of the normal distribution, but we are not going to say. We're not going to show this formula here. Suffice it to say that this formula produces the curve of the normal distribution that I presented earlier. Before digging into more details of the normal distribution, let's consider one more digression: the z-scores. So the z-score is calculated as follows. Z equals some value minus the mean from which that value was obtained, and then we divide that by the standard deviation. So if we've got a sample of number of values, and the first table is showing only 5 of them, but there are more values in this sample, but I'm showing in only these 5 for illustration. The mean on that sample is 40, standard deviation is 10, so the equivalent z-score for each of these x-scores is as follows. For 20, the score is -2. Why? Because we do 20, which is the value of interest in this case, minus 40, which is the mean, and that is -20. And then -20 is divided by the standard deviation. The standard deviation is 10. So -20 divided by 10 is -2, and that is a z-score. With z-scores, what we can generate is a standard normal distribution. Why is it called standard? Because when we divide by the standard deviation of something, then those values are called standardized scores. Okay, what I want to show you is that we can have different means, different standard deviations, like in these other cases, and if we apply the formula, we obtain same result. So let's consider this example: the mean of 100 and standard deviation of 20. So if we do let's do 140 minus the mean, which is 100, then I get 40, and 40 divided by standard deviation, which is 20, that's equal to. With 120, we do 120 minus 100, that's 20. 20 divided the standard deviation, which is 20, that's then 1. So we've got this z-score of 1. And the distribution doesn't have to have only positive values, could be negative as well. In this case, the mean is also 0, but the standard deviation is 10 instead of being 1. So we can do the same calculation from raw scores to z-scores. Let's return to the normal distribution. In this case, in the x-axis, we've got z-scores as possible values. So when we got z-scores, we've got what is called a standard normal distribution. So in a standard normal distribution, the mean of the distribution is always 0 and the standard deviation is always 1. So we denote the mean of the distribution with the Greek letter mu and the standard deviation with the Greek letter sigma. These are the possible outcomes. These are the possible values, but as I mentioned before, it doesn't make sense to in a continuous variable to assign a probability to specific value. What we can do is to assign probabilities to intervals. Okay, so let's start dividing the normal distribution into intervals. And we can divide using two criteria. One, we divide the distribution in segments of equal probability. And the second criterion is dividing in segments with equal length. We can divide the sample space in different ways, but this having some equality is desirable. So let's start with dividing in segments of equal length.